I'm going to talk to you about a typical experiment that we will do involving a glass or perspex block and a ray of light coming out of a ray box, and just talk through the labelling, what's going on. We'll shine our ray of light from the ray box into the glass block. At the boundary where there's a sudden change in refractive index, the light will change direction. And then when it returns into the air again, because these two faces are parallel to each other, the light will emerge and carry on travelling in the direction that it was going before. So let's just quickly talk about the labelling of what's going on in here. We call the ray of light coming in our incident ray, and we call the light ray that has been refracted, so when refraction has taken place, this is our refracted ray. What's less obvious is that the point where the light returns back to the air, leaves the glass and goes back to the air, we also have refraction taking place. But in this case, again, it's that incident ray. For this particular boundary, we have an incident ray and a refracted ray. And so we need to just be aware of that. However, I'm going to concentrate on the first point of refraction and take away these labels. Something you probably noticed are these dotted lines called the normal. The normal is drawn perpendicular to any boundary, and we measure all our angles with reference to that. So the angle of incidence, the I degrees that's been labelled, that is measured between the normal and the incident ray, and the angle of refraction, that R degrees, is measured between the refracted ray and the normal. So what actually is going on? In fact, I'll just show you, before I do that, what's happening when you measure your angles. So what we need to do is place 0 degrees along the normal, and then we're measuring our angle like this. So I've drawn an angle at 45 degrees from the normal. And if I just move over here, I've got my lined up along the normal. I've got my refracted ray at an angle of about 20 to 23 degrees. This is worth practicing with your students. So what actually is going on to make the wave change direction? The wave is changing speed. The frequency is not changing, but the wavelength is. And I've got another diagram here just to lay over the top. And this is showing what's happening to the wave fronts inside the light rays. Your students will be familiar with wave fronts. They'll call them ripples. That's what you see on the surface of water if you create waves, or if you drop a pebble into the pond or something like that. So we have these wave fronts. They're regularly spaced because I'm measuring the wavelength and one wavelength apart. When the light travels into a medium with a different refractive index, then the wavelength changes. In this case, the refractive index is greater, so the wavelength gets smaller. The frequency stays the same. So we have a smaller wavelength inside the glass compared with outside, and the speed of our light ray is slower inside the glass block. In fact, it's about 2/3 of the speed in air. 3 times 10 to the 8 meters per second in air, 2 times 10 to the 8 meters per second in glass, and then back to 3 times 10 to the 8 meters per second in air again. That's used to calculate refractive index, and it's much easier to see the wavefronts if you are using a ripple tank, but the same phenomena is happening with our light waves as well.